Okay, so welcome back to another video. In today's video, we have the following improper integral. We have the phi root of x multiplied by inverse tangent of x divided by 1 plus x to the power phi quantity square dx, where phi is known as the golden ratio. So we have a well-known constant, and then we also have an inverse trigonometric function associated together to form our integrand right over here. So it's basically it's just rewriting our integral and then figuring out ways, the creative ways really on how we can actually do the substitution such that this makes our integrand easier, especially since we have like the root of x with the phi root, but we also have a inverse tangent of x. So obviously that's going to make things, you know, I won't say it's like so convoluted, but eventually the answer does come out nice. So with that, let's actually just jump in. Let's start off with using the following identity. So I'm going to note that, and you can actually verify this yourself, it's that 1 divided by phi is actually equal to phi minus 1. So with this, what we can do is we can actually rewrite the following term over here, the phi root of x, using the following identity. So the phi root of x is actually, if we write that in terms of exponents, this is just x to the power 1 divided by phi. And then we write this as, so doing the substitution, so we have x to the power phi minus 1. So with this, we can actually rewrite our integral. So I'll call this integral capital I, and then we have the same thing over here. Replace our phi root of x with the following substitution over here. So it's x to the power phi minus 1, multiply with inverse tangent of x. We divide this by 1 plus x phi and then square dx. Okay, so now let's actually perform a little u-substitution. I'm going to call this x, so we'll let x equals 1 over u, right? But then don't forget there's also the fact that we have the x variables over here eventually want to replace in terms of y, just like over here. So what you see is that what I can do is I can actually just let's actually, before I do the differentiation, let's do this. So we have x to the power phi. If I do that, then if I have to raise the power phi to both sides, so we have u to the negative phi. And then again, if I have a phi minus 1, if I do the same thing, phi minus 1, then we have 1 divided by u, and then phi minus 1. Then if I do the differentiation over here, this is dx, and then that's equal to, so the derivative 1 over u, that's negative 1 divided by u square du. So from there, we can actually perform our substitution. So we have the new integral capital I. Let's see, we have to figure out our new bounds. We have infinity for x, so we do this, that has to approach 0, and we have 0 over here x, so that means it had to be infinity. And then since we have a negative over here with the new differential, we're substituting, so I can just factor out that negative 1 and put that outside the integral. Then we perform our substitution. So we have x phi minus 1, I replace that with 1 over phi minus 1, so that will come once I get to the denominator portion. Tangent negative 1, or tangent, inverse tangent of x. Now we replace x with 1 over u, so this is 1 over u, and then we divide this by, so let's see, that replaces this will be u, and then phi minus 1, multiply with 1 plus x to the power phi, which we said that's u to the negative phi, and then square, and then of course multiply with 1 over u square du. And then simplifying even further, let's see, because we have to fix our bounds here. We have infinity as the lower bound and then 0 as the upper bound. That's not possible, so you flip that becomes negative, but then that negatives cancel each other out. So now we have infinity divided by 0. Let's see, so nothing changes in the numerator, so we still have inverse tangent of 1 divided by u, and then we divide this by, so u squared is going to multiply to here. So when I do this, if I multiply u square let's see, pretty much the u square has to be distributed into here since they both share the same degree. Since they both share the same degree, so you can write that as a product and then square. So really we have u times 1 plus u to the power negative 5, and then that entire quantity square. So if I just distribute the u into the 1 plus u to negative 5 distributive, so what we get from there is that, let's see, so let me just write this as u and then 5 minus 1 first, and then now once we do the distribution, we're gonna get that this is u, and then add this with u, and then to the power, so let's see, this is u, and then yeah, okay, so this will be a, the exponent would be 1 minus 5, and then that quantity square, and then du. So now what I can do now, next step, I can actually just multiply a u to the power 5 minus 1 to both the numerator and the denominator. So let's see, I, new integral, 0. Then so when we multiply this both the top and bottom, we have u to the power 5 minus 1, then multiply with inverse tangent of 1 divided by u. And then if I multiply that to the bottom, then that's become a quantity square. So u 5 minus 1 square. And then of course this is still the product over here, u plus u to the power 1 minus 5, and then square du. And now you can actually simplify this even further using that same method I talked about, where we have the base shares the same degree. If they share the same degree, you can actually just write that as a product and then that as a quantity square. That's what we're going to do over here, that same method. The numerator still stays the same, then inverse tangent 1 divided by u du. So let's see what we got. So we both have squares, the exponent specifically. So we have that would have to imply that saying u to the 5 minus 1 times u plus u to the power 1 minus 5, that entire quantity square. If we actually do some distributing, so I distribute this into this term, so that means this is actually just going to be that negative 1 will just cancel, just be left with u to the power 5. Okay, so let's see what happens if we do to over here. So share the same base with the degree, so it's basically just u to the 5 minus 1, and then add this with 1 minus 5. Those two terms cancel each other out, so you're just left with u to the power 0. Obviously that's going to equal 1, and then square du. Let me fix that. This is supposed, I usually like to write it center instead of part of the numerator whenever I write integrals. We've actually shown that doing this whole substitution, this integral that we were just given that we rewrote is the same thing as over here. So the trick here, what we're going to do is we're actually going to double the quantity. So this means I'm going to move on to the with a new marker over here. I'm going to switch to red this time. So now I'm going to have 2 times I, right? And so what I'll do is I'm going to add this quantity over here, and we're going to add it with this quantity over here. And remember I said that they're both equal the same. We just showed that through the whole substitution. And remember, we can actually just stick a dummy variable over here. So that's actually very nice over here. So let's see. Okay, so now we add our integral. So give me a second to before I go to the next step. Okay, so I wrote this out. Now what you can do is that we can actually factor this out. We can actually factor out the specifically the x to the power 5 minus 1 divided by 1 plus x to the power 5 square. So with this, they share the same bound, so this is why we can do this, and using the linearity as well, so that's also great. So we have x 5 minus 1 divided by 1 plus x to the power 5 square, and then this is being factored out with inverse tangent of x, and then plus inverse tangent of 1 divided by x dx. Oops, I'm missing extra parentheses over here. So this is where we need to calculate this, and if you can actually look this up yourself, but how about this? I'll actually prove the following identity. This is actually going to the inside expression over here is actually equal to pi over 2. So let's see if I can actually draw this. Well, not really draw, but write out this proof over here. So I'll say that we can actually make the claim inverse tangent of x, then plus inverse tangent of 1 divided by x, that's equal to pi over 2. Okay, so what I can do from here, so just say proof. What I can do is I'll let theta equals inverse tangent of x, right? So what I can do is I'll just take the tangent of both sides. So that means tangent of theta is equal to x. Also, I should say, keep in mind that we're dealing with the interval from between 0 to pi over 2. Okay, so with this interval over here, so now what I can do is I can actually use that identity and say that the tangent of pi divided by 2 subtract with theta, that's actually just equal to cotangent theta. Okay, in other words, cotangent theta is the same thing as 1 divided by tangent theta, but we also said that if we do the substitution, we said that tangent theta was equal to x, so that's just 1 over x, right? And now what I can do is I'll just take the inverse tangent of the extreme left and the extreme right, so that way we have pi divided by 2, subtract with theta, that's equal to inverse tangent of 1 divided by x. Then I'll just add theta to both sides, so then we have pi over 2 equal to inverse tangent of 1 over x plus theta, but we said that theta, plus theta, but we also said that theta is equal to inverse tangent x, so therefore tangent theta, or inverse tangent of 1 divided by x, and then add this with inverse tangent of x is equal to pi over 2. All right, so that proves that, let's probably just put a box just for, how about this? We just proved that this is equal to pi over 2, so now I'll actually justify this and say that this is equal to pi divided by 2. Okay, so I can just replace that. But since that's also because pi over 2 is a constant, so I'll just move that outside the integral. Yeah. I'll just move this outside the integral. So we have pi over 2, and then 0 to infinity of x to the power phi minus 1 divided by 1 plus x to the power phi square, and then dx. So now, last thing we need to do is we just integrate this. Now what I can do is I can actually just do yet another u-substitution. Let me also justify and say that this is still equal to 2i. Okay, so now let's actually perform another substitution. Let's call this t. I'll call t, and we're just going to set this equal to x to the power phi. Okay, now if I do the differentiation, so we have dt is equal to x, or excuse me, not x, this is supposed to be phi, then multiply with x to the power phi, subtract that with 1 dx. All right, so I can actually divide phi to both sides, that's the constant, so that means I'll just move this outside the integral, so this is pi divided by 2 times phi. Then we have our integral. Let's see, if we're doing the bounds, so let's see, if we do infinity over here, then that means t would have to be infinity, and if I do 0, then t would have to be 0. All right, so nothing's changed. So this just replaces here, so that'll just be a 1 on the numerator. And then let's see, this is 1 plus x, so this is 1 plus t square, 1 plus t, and then square dt. And this is actually easy to show, just again, do another u substitution, just let u equals 1 plus t, then du is equal to dt, and then this is easy to show that you'll see that this is just, I'll just write the constant from outside, and then this is just -1, this is divided by 1 plus t, and then integrate, and then evaluate your bounds from infinity to, or 0 to infinity. Now you can easily see that you plug infinity over here, this is just going to be 0, subtract, put 0 over here, so this is -1 divided by 1, it's -1, so 0 minus -1, so +1, so therefore you get that this is just pi divided by 2 times phi. And of course, we said that that was equal to 2i, so what I have to do, just divide by 2, and so you get that the final answer, I, is what we were given over here, is actually just equal to pi divided by 4 times phi, like so. And there we have it. Final answer in this box of our given integral. So yeah, that's pretty cool if you ask me.